So today I'm here to disappoint you by talking about structure and why in many situations our data are useless unless we've imposed some structure onto them. And basically how to go and spot the sorts of problems where we need to have this structural type of thinking. Does anyone here work for Amazon? Or a publisher? Former publishers? I'm going to give you a problem that sounds maybe a little bit familiar. You sell lots of products, and some of these products are in competition with one another. So perhaps you sell chips, or wine, or beer, or I don't know, books. And you're selling many of these products, and they are in competition with one another. So the question is, how do I set a price based on my analysis that is going to optimize the profits for my entire portfolio of products? So maybe we're going to, go and listen to Adam, and we're going to run some randomized controlled trial. We're going to exogenously vary some prices of some books and not others, and then see what happens. And from that, we're going to go and estimate some price elasticity. And from that, we're going to work out what is a revenue optimizing price. That's beautiful. So how does that kind of reveal itself? Well, we've gone and we've randomly changed some prices, and we get a curve that looks like this, a revenue curve. If the price is 0, then nobody buys your products. If the price is very, very high, not many people buy your products, but you're getting a lot of money for each time you sell a product. So somewhere in between 0, getting a lot of sales but making no money on any of them, and up here, making not many sales and making quite a bit on each of them, there is going to be some revenue optimizing price. If you know your cost structure as well, you can bake that in and get a profit maximizing price. But is it profit maximizing? Interesting thing with these sorts of portfolios is that we can perhaps go and decrease the price. This current price of this book here, this red line, is clearly to the right of the revenue optimizing price. How about we decrease the price of this, in this case a book, and see what happens? Now, when you're in the world of selling many competing products, you change the price of one of them and there is an equilibrium effect on your customers. Your customers are going to substitute away from some books that are similar towards other books that are similar. If you discount Dostoevsky, maybe the customers who would have otherwise bought Pushkin are going to start buying Dostoevsky. Okay? So let's go and see what the impacts of this is in this particular model. So we're on book 1 at the moment. Let's discount the price to $2, which is around the revenue optimizing price. Fantastic. Now what's happened? We're getting more sales from this product, and the elasticity is such as that we're increasing revenue for that product, where revenue shot up here, our revenue market share has shot up, the unit sales market share has shot up. But what has happened? Well, there are other products that I sell that have actually been cannibalized. Okay, so some of the share has come from the other products that I sell, and in some cases that the decrease in share is really, really big. Now those are the products that are similar. So again, think of this as being, I've discounted Crime and Punishment, and suddenly people who were otherwise going to buy War and Peace are now buying Crime and Punishment. So what happens? Well, the effect on the portfolio isn't clear. Although we've maximized revenues for this particular product, we've actually damaged our portfolio sales. Our portfolio revenues have decreased because we haven't taken into account, if we were to just optimize this price, we haven't taken into account the substitutions that really occur. Now, so this is kind of like leading with the punchline of my talk. And the punchline of the talk is there are many, many situations in which the data that we observe emerge from some competitive or preference-based structure, and what we observe is in equilibrium. And you can throw the biggest neural net in the world with 1 trillion data points and be precisely wrong about inference away from equilibrium. So we're going to talk today about the sorts of problems, how to spot these problems, and a couple of other things. So let's jump into it. Now, before I get into that, though, we'll talk about what is our toolkit? What are data scientists good at? And where does value get created? Because I think that we should really be trying to maximize the amount of value that we create. How do we productize this sort of framework? And how does decision theory and structural modeling fit into all of this? So, has anyone here worked as a management consultant or worked with management consultants? Management consultants love quadrants. One of the quadrants they love is this one here. If you're trying to, what is expected impact? Well, it's impact multiplied through by probability of success. And impact, you're going to come up with some idea of how to quantify that. And probability of success, you need to go and quantify that. But it is a product. This is an expected value. So we multiply some function by its probability density. Now, this quadrant here, I'm sorry about the resolution. On the x-axis, it's additional impact of success. Keyword is additional. We don't want to rewrite MS Word. We want to do things that haven't been done yet. You could have a lot of quote-unquote impact by rewriting MS Word entirely, but your additional impact is zero and no one's going to pay you for it. You want to do something new. Same time, you've got probability of success. Now, you can think about the tasks that you do on a daily basis as falling somewhere in this quadrant, or in these quadrants. You don't want to be working in the bottom left-hand quadrant. These are things that you're not going to pull off, and even if you did, they're useless. Okay, I've spent a lot of time down there. I think last night I was plotting war deaths, having an interactive plot of war deaths through time. It's up here we've got tasks that you're likely to be able to do easily and are going to have a huge impact if you do them. This is where you should be focusing your time. The question is, what do our tools actually allow us to do that are both impactful, that we have a pretty high confidence of success? Now, this is where you're going to hate me. Not yet. You can hate me in a second. Let's firstly talk about the x-axis, which is the the y-axis, probability of success. What things are we good at? Now, I would say the thing that we're probably best at is, or at least in theory, is when we've got some outcomes. That might be, outcome could be winning a game of Go or chess or something, or classifying a picture. We've got a set of inputs, or a state. The state could be the position of the pieces on the board, or the pixels in an image, and where the probabilistic outcome of the outcome is entirely defined by the initial state. Okay? So with Go, all the information in the system is on the board. The feelings of the analyst have no relevance at all. What's happening outside, the weather, no impact at all on what's happening in a game of Go. It turns out that for such systems, we now have technology that is growing at such a rate that essentially any problem of this sort, it's only a matter of time and processing power and whether Jan LeCun works on it. Okay, so if those guys go and work on it, they've got enough processing power, then it's done. At the other end, going down, we've got things that we're pretty good at, which is when we've got robust signal and we're just making straight predictions. Okay? We're not making any predictions about counterfactuals. We're just making plain expected value predictions where there is a robust signal. Data scientists are pretty good at this. Going down further is, we're in the good side of this, we're really good. The bad side of it, we're awful. But it's causal inference, hopefully with experimental data, sometimes with observational data. Here I'm trying to start to think about counterfactuals. I want to know what happens when when Adam flashes changes the title of some BuzzFeed article, whether I'm going to click on it. He can go and randomly vary that, and sometimes I am more likely to click and other times I'm less likely to click. But because it's a fairly controlled system and Adam's a really great causal inference guy, this is a pretty solved problem. Going down way the other end, you've got a lot of psychology, observational economics, all this sort of stuff where, think about macroeconomics. Unfortunately, we can't go and exogenously vary the monetary policy rules. We can't go and change the interest rate willy-nilly just to see what happens. Maybe we should, but I'm not sure we can. Now, where we get really, really bad is incorporating uncertainty into decision-making. This is very, very, very important. And yet, we seem to be very focused on first moments and not so much on higher moments. We should be taking those uncertainty, both in our model and in our predictions, into account when we make decisions. And what we're really hopeless at, is what my talk is about, is when we've got a system with many agents who have the following structure. When you've got multiple people, and they all differ, and they all have their preferences, and they all have their constraints, and they're all optimizing given their constraints in such a way that we observe some outcome. So this is where we really, really suck. Whenever we want to do any counterfactual analysis of this, you need to build a model, and data scientists, or most of them, unless they've come from one or two little sub-disciplines, are hopelessly ill-equipped to do this. It doesn't stop them from trying, but most of that analysis will be pretty bad. Okay, so that's what we're good at. Any disagreements? Very good. What adds value? Now, I like to think about the sorts of things that add value as being whether they impact a growth rate or whether they impact they have a step change sort of thing. Technologies that have a step change sort of character to them, these are ones like a word processor. You build a word processor. Yes, look, I understand Word gets better every year. It's mainly marketing. The step change is not using a typewriter anymore. It's being able to do formatting and stuff in a WYSIWYG environment. It's a huge step change. But once it's built, it's kind of a step change. Another example might be chatbots. We're not very good at chatbots yet, but once they get good, we're just going to get rid of call center operators, and we're going to have chatbots. And that's going to be a step change, and some people are going to get extremely rich with these chatbots, and then that will just be the new norm. Now, I'm not saying that these sorts of step change technologies are bad and you shouldn't be working on them, but over time, the sorts of things that make at least some countries rich and some countries poor and some businesses phenomenally wealthy and others less wealthy is changes to the rate of growth. And that rate of growth might be things like the ability to execute on these step changes, but I'm thinking like being able to hire excellent people, being able to think about what your opponents are going to do and preempt them and have strategic decision making. These things affect the growth rate of value creation. And that's why CEOs and C-suite executives get paid millions and millions of dollars. That's why entrepreneurs make such a huge amount of money, because they can create value by changing the growth rate. So, I don't know what we should prefer. I know we're probably better at this one. But I think if you were to observe a country or a company for a very, very long period of time, all the differences are in this. It's not in this. So let's maybe prioritize some data science effort. Down in the bottom left-hand corner, we've got 10-day weather forecasts. It's basically impossible. It's a chaotic system. Don't bother. Even if you could do it well, it's 10 days. Like, we've already got pretty good 2-3 day forecasts. Who's making 10-day weather decisions, like decisions based on weather forecasts? It doesn't matter. Don't bother on, don't do this. Up there, automated art. We're pretty good at this. We can get, various neural nets to produce paintings or whatever. It's completely useless. Why bother? Up the top, things I'm really confident that we're going to get pretty soon, based on trajectory and the fact that these are problems that are defined by the inputs. We've got autonomous driving by computer vision or X-ray classification, these sorts of things. They're closed systems. They've got pretty high quality information. These are solvable problems. They're maybe not easy problems, but they're solvable. Bottom right-hand corner, Or maybe let's talk about Clippy first. And I'm thinking about things like Alexa. You may have noticed that you can't understand any word that I say. This is because I'm from a country on the other side of the world called Australia, and Alexa can also not understand a word that I say. I was crashing at a friend's place the other day, and I had a talk in the morning. I had to get up at 4:30 to write the talk that I was giving in the morning. Alexa, turn the lights on. I cannot understand you. It was actually blaring out a pair of bookshelf speakers, so they really hated being woken up by Alexa at 4:30 in the morning. So next-gen Clippy, Alexa and the like, might be a really great technology. Maybe it's really good, maybe it's doable, I don't know. My experience with these sort of technologies so far has been pretty hopeless. It's almost always easier to turn on the lights yourself or flip open your iPhone and do stuff. The things that I'm really interested in are down here. Now, I don't think that we can do equity price prediction. We can maybe do pretty good prediction of second moments, so volatility of stocks, but doing first moment predictions of equity prices is, at least in the short run, is pretty hopeless. Maybe in the very, very short run, kind of the high frequency trading people might have some good signal. In the very long run, maybe, but in the short run, it's hopeless. Using uncertainty in decisions. The great thing about using uncertainty in decisions is we've already worked out how to do it. There have been people working on this since the 40s, or even earlier, but really formalized a lot of this sort of thinking in the 40s. And there is already a huge theory about how to do this. Now we have the tools to properly quantify the posterior distributions for our unknowns in fairly large and complex models. This is something that is now possible. And Eric over here runs a company that is doing exactly this. You should go and talk to Eric. Things like automated HR. I think this is one of the really big games big payoff games in data science, because you can potentially add a huge amount of value by improving HR processes. This is how you get good people. This is how you have a high growth company. And the problems aren't insurmountable. It's mainly data cleaning, network, exploring networks, all this sort of stuff. These are things that we're actually quite good at. The thing that I am really fascinated by is automated corporate strategy. I'll give you a couple of examples of what I mean by that later, but this could come down from using data tools to help conceive of a new product. What product should I create? And everyone knows the kind of House of Cards story where people liked, was it political thrillers and Kevin Spacey? I know you're not meant to talk about Kevin Spacey today, but House of Cards apparently came about because analysts worked out that people really liked political thrillers and Kevin Spacey, and it's like, whoa, let's put Kevin Spacey in a political thriller. But there are probably more complex sort of problems that we can solve with quote-unquote automated corporate strategy. That's where we learn a lot from game theory and use those game theory to help guide how our models work. So I trust you're all Miyazaki fans. Has anyone seen this video? There's these guys who pitch Miyazaki on an AI that generates animation. Miyazaki is probably the greatest animator of all time. I would never wish to incorporate this technology into my work at all. I strongly feel that this is an insult to life itself. So don't do this stuff. Okay, so the other thing is that location, where these types of technologies sit in this quadrant, is not static. It's a function of the technologies that we have. As technologies grow and change, then maybe some things that were infeasible become feasible. Maybe as technology grows, the impact of a Clippy, a good Alexa, grows. Maybe it really, really helps disabled people, just not ones with an Australian accent, but maybe these things are going to move around. And so having some foresight about how technology changes are likely to affect the position on this chart is really going to steer what sort of things you're going to be working on. Okay, so let's go into two of them a little bit more deeply. The first is decision theory. Decision theory, it turns out, is pretty simple. So then we'll talk a little bit about structural modeling. Okay, so decision theory is basically you want to do things that maximize the expected utility of a choice. Okay, so you can think of each person considering a perhaps countable, perhaps uncountable set of choices, and this might be that uncountable set of choices might be a continuous price for a product. Okay? We're going to condition on a whole bunch of unknowns. So if you're choosing price, and C here would just be a price that we're going to choose for selling a good. Theta is a set of unknowns. That might be the price elasticity or something else. A bunch of unknowns in our model. We've got some data, Y, that we've observed in the past, maybe from an experiment, maybe from just observing historical sales. We've got a loss function L. This loss function L, for any values of the unknowns and for any choice, we can assess the value of that loss function. Now, we really should be a little bit careful in talking about loss function because this is a really important part of the step. You need to elicit what decision you're actually making. A great example of this is an old colleague of mine, Andrew Landgraf, who won the NCAA challenge on Kaggle earlier this year. So how did Andrew win the NCAA challenge? Well, he worked out that the idea of this game is not to just predict which teams are going to win. The idea of this game, and that would just be a loss function on your position classification, your classification quality. The idea of this game is to be the highest ranked position on the board when there are lots of people following various strategies. So sometimes what that means is that there might be a team that is 49% likely to, the probability of them winning is 49%, and the probability of the other team is 51%, but because everyone else is modelling that other team 51%, they're all betting on that team. And maybe what you ought to be doing is betting on the other team, and that's going to, in expectation, increase your rank highest. So eliciting this loss function is the important thing in this task. Well, one of the important things. The second one is that you actually need to be uncertain. You need to have well-calibrated uncertainty about the distribution of your unknowns given the data that you've observed. And that's what data scientists utterly fail at on the most part. Mostly, we have point predictions. We're using optimization techniques to back out what the most likely candidates for theta are. And we have no uncertainty about those, and we're just going to not be able to assess this posterior at all because we don't know it. The beautiful thing is that then our choice, if we have all of these things, our choice is simply the argmin of this very simple integral. So it's a weighted average of the loss function over the joint distribution of the unknown. That's all this integral is. And we can assess what this integral is for all possible c's, and we just choose the c that maximizes that, which is actually quite simple. Computers will do this for us in seconds. So the problem with, as I mentioned before, is that most data science techniques, all your machine learning techniques, all your neural nets, as soon as you're not using Bayes, you're not getting any distribution over your unknowns. You're getting point estimates at best. Sometimes they're awful point estimates, especially in high-dimensional problems. Decision theory requires that you're honest in your uncertainty about the unknowns in the model. So if you're getting point estimates, you just can't do this. Okay, so let's go through a little example. We'll say we're estimating a fairly rare event that occurs with some probability specific to the data, theta. So the firm I work for, we lend money to alternative lenders in sub-Saharan Africa. So microfinance banks and asset lenders, cow lenders, these sort of things. Now, one of these sort of businesses, they're all going to have some model of risk of all the people in their portfolio. And you might think of, and let's say a cow costs $2,000. They lend out a cow, and you've got some loan attached to that cow, and it's a balloon payment at the end. Now, you observe how much milk that is coming from that cow each fortnight, every 14 days, and you try to infer the probability that that person is going to default on the loan. They're not going to pay it back at the end. Now, let's say if that probability goes above 50%, I'm just going to take that receivable and I'm going to sell it off to a collections agency for $1,000. And let the collections agency deal with trying to extract more than $1,000 out of the customer, the end borrower. So if probability is greater than 0.5, I'm going to quote unquote spend $1,000. I've loaned out $2,000. I'm going to take a $1,000 hit. Otherwise, I don't spend anything. So, two ways that we might do this. The first is that we build a classifier to estimate, we take a random forest or something to work out what the probability of the person defaulting is, given how much milk we've seen. The second way of doing it is we build a Bayesian model. Now, the question is, under these two approaches, how does the loss provisioning differ? And loss provisioning, for those not in finance, is when you hold a bit of money aside, or you allocate, in an accounting sense, some money aside just to take, just in case that happens. Okay? So that you don't overstate the size of your book and load yourself up on debt based on a book that never really materializes. So here are three different densities for the probability of the person defaulting. The first one, that black line, has an expected value of 1/11. The second one, the red curve, also has an expected value of 1/11. And this Dirac delta, this spike, is also on 1/11. So let's say we've got three models and they all give us the same expected probability for this person defaulting. Now, this one here, the spike, that's coming from, say, a random forest or something that's giving me a point estimate of the person's probability. The other two are giving me distributions over the probability. So I'm uncertain about this probability. So what I can do is I know what that loss function is. This describes my loss function. So if I work out the integrand, which is simply the loss function across the probability density, well, here it is. So you can see the one that's this black curve here has a really fat tail, and the weight it gives above here, we're going to multiply, or give weighted sum of this, of the cost, which is $1,000 if the probability goes above 0.5. The red curve gives far less weight to a probability above 0.5, and so we give much less weight, much less negative utility here, or much less loss here. And of course, this spike here gives no weight at all to a probability greater than 0.5. And so we're not going to provision any losses at all. So three probability estimates, three different losses that we're going to provision on. So the first one, probability is less than 0.5, so the expected loss is 0. Tighter posterior, expected loss is 10 cents. With the looser posterior is $1. This is not a huge difference. Of course, there are situations where, when you're talking about extinction events, nuclear war, these sorts of things where we might want to actually take some cost to stop a negative infinity sort of outcome, this whole Pascal's wager sort of thing for the religious people in here. These large negative values can really matter. So that's decision theory in a nutshell. The second part of the talk is, when I say part of the talk, here we've got a few minutes, is that we want to build structural models. Now, so what is a structural model? We've got, as I said before, we've got a whole bunch of economic agents. An agent could be a person, a firm, a government, whatever. Each of those agents is trying to maximize something. Okay, they've got some preferences. They care about things, and the things they care about are likely very, very high dimensional. what are you maximizing? Well, you're not just maximizing money. You don't want to spend too much time at work. You want to spend time with your family. You want to go on a couple of holidays a year. You really love Japanese food. Like you're trying to maximize a high-dimensional object. Okay? Now, when you've got a whole bunch of these actors, then you can have some notion of equilibrium. So you need to think, what is the mechanism by which these people, or actors, firms, governments, whatever, come together and they might bargain, or they might write contracts, or they might have sales or whatever that result in the data that I observe. A great example I just came across the other day of the sort of problem that could be answered with a structural model, and why we might want to think about this in a non-economic setting, is a friend of mine who was asked to do some analysis of, you've got planes on the runway, and they're taxiing about, and this person was asked, could you do a ranking of potential policies that could reduce the probability of having accidents on the runway, having two planes crash into each other? Okay, difficult problem. Why is that? Well, how many planes have you ever heard of crashing into each other on the runway? How many affirmative cases do you have? How many planes take off every day? How many planes are on the runway every day? You have essentially 0 affirmative cases. It is really difficult to assess the change in probability of an accident when you have 0 affirmative cases in your data set. So you're going to have to come up with some structural model. You're going to have to come up with an idea of how pilots and air traffic controllers are making decisions, and see how changes to the structure, changes to the rules, changes to the layout of the airport are going to affect that decision making. That's the only way you can really do this in an analytical setting. Okay, so when you've got a whole bunch of these actors and they're all doing what's best for them, or something approximately good for them, what we get is some quote-unquote general equilibrium. All observations are made in equilibrium. So that is, you can't just throw some neural net at equilibrium outcomes of such a system and expect it to perform or say anything sensible at all if you were to perturb one of the inputs into that system. So if I were to change prices, or if I were to change the rules or anything like that, your model's going to say something stupid. And one of the classic cases you get with price elasticity modeling is when you go and estimate some big predictive model on this and find out that when you increase prices, well, sales will increase, as in the number of units sold will increase. That's a classic finding, because a lot of the things that drive prices also drive sales, fashionability or advertising or whatever. Okay? So if you are working with a system where your observations are coming from such an equilibrium, where there is some game or some market that brings together people, and the data that you have emerge from this equilibrium, and if you're not using theory, your model's bunk, and you need to do something else. So a fun example in Australia is all of these routes in the desert. So we've got these regional centres, and I spent a fair bit of time in Darwin, which is up in the north. It's near Indonesia, kind of tropical town. And you go to the airport in Darwin, there are all these guys in like fluoro jackets and big boots, like steel cap boots, and they've got big beards. They look like the sort of Australians that you want to see. They smell like rum. They're all flying to these little towns, and these towns are in the desert. They're ore mining towns, mainly iron ore. Now, the people paying for their flights are not them. The people paying for their flights are the mining companies. If you were to go and try and work out what the optimal price is for one of these flights, what you might do is randomly vary the price. That's a great tool that we've got, exogenous variation of the price. And what you would find in a small, limited experiment is that you're going to sell just as many tickets, because the mining companies need to have boots on the ground. So, well, we're like, they don't care what price I set. Well, let's profit maximize, let's jack the price up. And yet, what we have observed in equilibrium are prices that are not crazy. When you go and look at how much those flights cost, they're not crazily expensive. It's like, what's going on? Are these airlines leaving like $1 million bills on the table? Is that what's happening? Of course not. The people who run these airlines are not dumb. What they realize is that there's something called contestable markets hypothesis. If you have an airline route that can be competed by any, if it's open, if there's no legal monopoly that's being granted to the existing incumbent, anyone can fly that route. And if they were to jack up their prices high enough, they're inviting competition. And as a consequence, you have never observed the counterfactual of what would happen if you were to increase the price permanently. Okay? So what we've got are equilibrium observations. Those equilibrium observations often don't come from people running the numbers. They come from people who have deep understanding of theory and industry. Another example, which comes from my work, is in pricing loans. So one of the things that people do, especially with like bulky purchases, is they'll buy them on credit. So it might be they might buy a car, or they might buy some furniture, or in the case of one of my customers in sub-Saharan Africa, they lend out motorbikes, and these motorbikes are paid back over some time. Now, how the scheme works, it's not a scheme, sorry, how the contract works is that you pay some fixed proportion of the face value if you were to pay cash today. But you get that same price for the first, I think it's about 10 months is their contract. If you were to pay it off within 10 months, then you get the today cash price. It's about 78%, I think, of the full price that you could possibly pay. After 10 months, this is the red line up top. After 10 months, some interest starts kicking in. If you've ever bought one of those furniture sort of deals where you get the cash price on day one, you know you need to pay it back the day before your interest starts kicking in. Otherwise, they'll charge you some large amount of interest. Okay, so then interest kicks in, and you need to have paid off by the end. So when you observe the actual payments of customers, they look like this. These black lines up here, there are many black lines. Everyone's paying off the minimum amount. Sometimes people have an accident. These are motorcycle taxi drivers, so sometimes they have a crash. They're given a month leeway. But they start repaying, and then you see a whole bunch of people, they get to month 10, and they make that last payment. They pay it off because they don't want to pay the interest. As people keep on progressing, more and more people have enough liquidity to pay off the loan. And you get lots of people. Something like half the portfolio engages in this sort of behaviour. The other half just pay off the minimum payment until the end. Those people are paying about 20% more than the people who pay off at the beginning. So why am I telling you this? Well, what we can do is say that these decisions are made optimally given the borrowers' behavioural parameters. In this case, their discount rate. Okay, so discount rate is how much you don't care about the future. If you've got a high discount rate, you don't care about the future. People with a low discount rate do care about the future. So it's likely that people who are paying off at the beginning have a low discount rate. It's likely that people at the top have a high discount rate. We can actually back out these structural parameters, the distribution of discount rates across the population, by specifying a model. And then what we can actually use is to use that model to help us design new financial products. For instance, what happens if I decrease the cash price proportion? What if I push the month of discount out? Let's extend it to a 22-month term. Let's say the outside interest rate, the rate that they can borrow from other banks, increases. The unit price decreases. So now I've got some model, I've changed multiple things, not just one thing, multiple things, and it's a structural model, so I can run simulations. And my computer is running these at the moment, it'll be a bit slow. Then eventually Shiny will update, and I can see what the impact on my internal rate of return for the portfolio is going to be. There we are, we've dropped out internal rate of return about 1% per month. So that is a fun little example of a structural model in practice. Finally, what sort of things should we be considering when we put these into products? Like, what we excel at is turning data science into products. That's our forte. Unfortunately, structural modeling requires that you have some domain knowledge, requires that you can understand a problem quite deeply. You can't just throw a tool at it. So this is a really big concern. What we're good at, though, is productizing. I think that, I am personally working towards these goals. I know Eric and Dan are working on these goals. Adam's done a whole bunch of stuff, writing libraries to try and productize a lot of this sort of stuff. We also, one of the things that we have is this much better knowledge than economists of how to, turn, or what sort of interesting nonlinear models we have. Things like splines, things like trees, things like neural nets, whatever. We can use a whole bunch of techniques that are essentially curve fitting, and I think we can do a lot better than a lot of economists who aren't so familiar with these techniques, and so they're kind of assuming linearity everywhere for a lot of the structural parts of their models. So we can do better than that then. And yet the one thing that we really, really need to do to become good at this sort of thing is to invest in getting that outside knowledge, that knowledge that experts have. You need to go out to lunch with people. You need to try and elicit the information from them in a smart way. So that's my talk. It's my spiel on structural models. Any questions? We've got like a minute and a half. Thanks.